Okay, cool. Hello. Shall we? All right, so it's 3:11. Let's get started. Welcome to Lecture 5 for CS61BL. Hope you're all having a good time working on probably your project. I see that's why everyone's got their laptops out. But yeah, so before we begin, here's some quick announcements. As always, we've got our live lecture thread open at 772 on Piazza. And then, in case anyone missed it, there's a project 2. It's due this Friday at 11:59 p.m. So the auto grader is up, and we have increased your token count so that you can submit more often. However, please remember to keep testing locally. The auto grader count going up isn't so that you can necessarily test whether your entire thing works repeatedly, but more of oh, I forgot an S and something, and that's why it's not printing out correctly. So it's for tiny mistakes like that. But you do have the increased token count, so that's nice. Other thing to note, so as we knew before, Friday's lab was going to be a project work day, so you can make your finishing touches on Gitlit. However, Thursday's lab has also been converted to a project work day, so yay, more time and less other things to think about. However, the lab that was going to be on Thursday will still occur in the future, so you still have things to do. Okay, just some reminders. Quizzes, they're still on Fridays, even if it's a project work day. There is a quiz every Friday, so make sure you show up. You'll take your quiz, and then you can work on your project. Don't just think, oh, it's a project work day, I don't have to show up. I mean, you could, but then you don't get your quiz points, and that's really on you. Aside from that, if there is no lab on Friday, we still have self-reflections, which are worth part of your quiz grade. So you actually get free points almost for taking your self-reflection, and it counts towards your quiz grade. So yay, now we can boost our quiz grades. Other than that, there is a mid-semester survey due on Friday. If we get enough participation, you can get credit. So there's really no harm in taking the survey and getting extra credit because, who doesn't love extra credit? And then something that's a little out of our control, Gradescope, where you submit your project, will have maintenance that's been scheduled for a while, and it's scheduled on July 28th at 4 p.m. all the way to July 29th at 4 a.m. And if you notice, that is in the period that late period after projects during the 50% penalty. So all of the auto grader is going to be unavailable during that time. So you've extended the late submission during that time, so you can submit your project for the 50% penalty all the way up until the midterm. But ideally, we get it all done earlier than that so we can study for the midterm. But, things happen. So you have a little bit of an extension there. Cool. Any other questions on the announcements? Awesome. So we're going to move on. So last lecture, I was talking about this thing called game trees, which I think are cool. And so I'm going to keep talking about them. But what happened last time is I didn't get quite enough time to finish it off. So we're going to review what we saw last time. This time it's at the beginning of lecture, so we're all awake. And then we're going to extend it and really talk about the mechanics of this thing called alpha-beta printing that I got into before. So as a refresher for game trees, I was talking about this idea of generating and testing, which we saw a little bit of in last Thursday's lab with the iterator, where we basically weren't iterating through something that necessarily existed, but we were iterating through possible game states that we could enter. So game trees kind of model something like that, where we have possible game states. So instead of just storing something in a data structure and then going through things that we already have that exist, we're going to generate stuff that fits some category. So we say is there an x such that p of x, and we'll save certain values. So for our iterator, we said, is there a move such that it's valid and I can take it? And those are the things we would iterate through. We wouldn't store our invalid moves. We just kept track of the valid ones. And those are the game states that we could move into. So then, since we don't necessarily, say you have an even larger game where you don't even know how many moves there are, overall, you're going to at least start by saying these are the moves I have access to and start enumerating them. And so once we have a certain list of moves that we could make, we can go through them and test and see which one's better. So theoretically, what we'll be able to do by the end of the day, if we want to, is take these ideas in alpha-beta pruning, and you could make a mini AI that could beat you every time in that game that we learned in lockdown. because we could use alpha beta pruning and the AI would look through all the best possibilities and at worst case it would probably tie you or something. Bless you, Christine. So then, yeah. So what we can do is to keep that like AI that we might come up with from taking a really long time, we're going to try to cut out possibilities that we don't think will be useful to us because there's no chance that we'll ever take them. So this is just a refresher on the idea of game trees. So we have like two types of nodes. We have maximizers and we have minimizers. So here are like, if I am like the one playing, then I want to think of things from my perspective, because when you're playing games, you kind of have like a very selfish perspective because you want to win and you don't want your opponent to win, and that's just how games work. So we think of it as like, if I am taking a move, I want to like maximize my points, and then my opponent wants to minimize my points because, you know, they want to win, and them winning is the equivalent of me losing. So we have basically each node represents like a current game state, and then if we take one branch versus the other branch, then we're like making a move and entering a new game state. So these could be like the different valid moves on our lockdown, or the different moves in a game of checkers or chess, or something like that. Or like in tic-tac-toe, like you can move in some spot. So then there's my nodes, which are maximizers, and my opponent's nodes, which are minimizers. So then what we'll do is we'll say like maybe this game only has like a couple moves where I make a move, my opponent makes a move, I make a move, and then my opponent makes a move, and that's like the entirety of the game. Then this is as deep as this game tree will go. We'll basically say at these bottom nodes, that's where your opponent gets like they make some move which has some value. If this was a larger game, then this tree could go much, much further, and then it might take a lot of time, because like if it branches out a lot and we have a lot of layers, you might not have enough space on your computer. So what you would do is you would kind of like cut off the tree at a certain layer and like estimate the state of the game. So we talked about that a bit last time. So then what we're going to do is to figure out which move I should make, we went through this mini-max idea where we said, okay, I'm going to look towards each direction and think, okay, which is the best way to go? And so what I did here is I said, like, let's pretend that I had already taken this like left move here, and then my opponent had taken the left move. Then which move would I want to take from there? Choosing between -30 and -5. If I want to maximize, the max of -30 and -5 is, someone's got to know it. -5, I heard it. Wonderful. Math class. That's today's math. Okay, so yeah, we get -5, and then suppose my opponent take the other move, then the max of 5 and 15 is, beautiful, it is 15. And then we continue for all of these, and then if we want to see what my opponent would want to choose, so basically what we know here is like if I were given the choice of these, I would choose the right branch, and those I would choose the right branch, and then the far end I would choose the left, and then the right. But so to see what my opponent would choose, I then take the minimum, right? So what's the minimum of -5 and 15? Yes, you got it, it's -5. I know you all were dying to throw it out. And so on the other side, you also get -20 and 10, and you see the minimum is -20. And so ultimately, I say, okay, look, if I go to the left, my opponent's going to attempt to force me to a value of -5, and if I go to the right, my opponent's going to force me towards a value of -20. Do I want to lose badly or really badly? You probably don't want to be embarrassed too much, so you just want to lose badly, and you choose to go to the left and just kind of lose. Yeah, so does that kind of make sense, how we go through this? So we kind of like populate the tree all the way back up. So what's interesting is that we didn't actually have to look at all of the values in here in order to arrive at this answer. And that's this idea of alpha-beta pruning that we kind of touched on last time. So here's alpha-beta pruning, and it's this like hand-wavy approach at first so that you can kind of get the idea. But so the idea is we want to like prune off options that we know that we'll never ever take. So what we'll do is we'll come back down to this front area, and we'll say, okay, so I get to this maximizer node, and I'm going to choose a max of -30 and -5, and the answer is, we just did this. I mean, come on. -5, right? So we get -5, and we say, okay, I, the maximizer node, have gotten the opportunity to choose this -5, right? And so what I'm going to do is I'm going to tell my parent, this minimizer node, that like, hey, like you can choose me, and you'll get -5 if you choose me. Like just know that if you choose me. So now the minimizer node says, okay, well, since I know I can arrive at -5, if I have as many children as I want and any other like values that could be there, am I ever going to choose one of my children that will return a value greater than -5? No, right? Because I'm a minimizer and I want to get to -5 or like less, right? So what will happen is that minimizer node will tell its next child and it'll say, hey, go ahead and look and see what possibility you can come across, but if you arrive at anything like greater than -5, know that you're worthless and I don't want you. Yeah, so what it'll do is it'll tell its child that, and it'll say, okay, now that this child knows the circumstances under which this parent thinks it's useless, what it'll do is it'll look and it'll say, okay, I've gotten to this value of 5 here, right? And I look at it and I say 5 is greater than -5. And I know that since I'm a maximizer, I'm not going to choose anything less than 5, right? So what it'll do is it'll say, well, I've arrived at 5. I know that my parent won't want me if I'm greater than -5, so I know that I'm unwanted. So what it does is instead of looking through the rest of its children, it says, okay, well, that's it. Gone. I don't need them. And it doesn't look through the rest, right? It says there's no need because no matter what, I'm never going to choose something less than 5, and 5 is already greater than -5, so let's just throw away the rest of the possibilities. Yeah? Okay, we're following. So then we do the same thing on the other side, and so what we would do is this minimizer would pass up the value of -5 to its parent, and I think I messed up that animation, so it's gone. But theoretically, the ultimate maximizer parent would know that it wants to get -5 or above, and then it would tell its minimizer, which would tell its maximizer, and we come all the way over to this like next empty green node, and we would say, okay, this maximizer knows certain things, right? And it knows that like it can collect values of like -20 and -30, and it'll get the maximum of those, and it'll pass those up to the minimizer, but the minimizer knows that its maximizer only wants a value that's greater than -5. So since the minimizer has the option of getting -20, it has no need to look through the rest of its children because it's only going to get smaller than -20, and thus it's not going to get chosen. So then we can do the same thing on a larger scale and prune off all of these options here, and then we can go ahead and say, all right, maximizer, you can choose between that -5 or this -20 that I know won't get chosen, and then we end up choosing -5. Does that kind of make sense? It's like kind of hand wavy and saying like, oh, it's all about what your parent thinks and the child thinks and like passing that around. So let's try to like solidify this idea, yeah? So what we'll do is let's look at a smaller idea, but we have like, we're just gonna go through like the smaller example at like why this works. So at the beginning, this is just the left like subtree of our former example. What we'll do is we'll start at the minimizer and we'll say, okay, this minimizer knows nothing, and then like none of the nodes know anything right now, and then the maximizer now knows that it can get at least -30, and then it looks at -5 and it says, well, I can get at least -5, and then it says, okay, since that's all my children, I'm gonna pass up the value of -5, and now that one, the minimizer knows it can get at most -5, so it's not gonna try to get any like larger than that, right? Then the maximizer says, I know I won't be chosen if I exceed -5. I receive the value of 5 and say, well, that's bigger than -5, I can prune off whatever's left. And then I just go ahead and pass that value up and I choose -5. Any questions so far? Cool, either really good or really bad. Okay, so then the way the overall search algorithm works to like make it more like mechanical so that you could actually code something like this is we basically say, so depending on whose move it is, and that's like the nodes, right? Either the maximizer or the minimizer, we say we're going to search for a move estimated to be optimal in one direction or the other. Or if we have like more options, maybe there's like 3 or 4 directions we could choose. So this isn't actually limited by having a binary choice of which way you can go. You can have multiple options. But so what we'll do is we'll say we're going to have these things called alpha and beta limits, right? And this is what's going to let us actually like pass down that knowledge of what our limits are instead of just kind of saying, well, the child knows and the parent knows, right? We don't have to be quite that hand-wavy. So what we'll do is we'll say the maximizer, the high player, does not care about exploring a position further once he knows the value is larger than what the minimizing player knows he can get, because the minimizing player will never allow that position to come about. So whatever that whole thing meant like formally is pretty much what I was saying before of like if my parent has told me not to go past this limit and I go past that limit, then I know that I'm not going to get chosen. So that's how it works on one side, and the same thing vice versa on the other side, right? So we basically have our parent pass us a limit down, and then if we cross over the limit, we know that there's no point in going any further. So the maximizing player always wants to find the maximum, and then you always start with these alpha beta limits that we'll talk about. They're going to start at like negative infinity and positive infinity, and then the minimizing player would start the same way, and you just start wherever your current position is, and you find the max or find the min based on what your player is. So we're getting like closer to the pseudocode. But so, just to explain what happens, so we say we're going to have alpha, which starts as negative infinity, and we have beta, which starts as infinity. And what we'll do is, I messed up the animation again, but that's fine. That -5 is not there right now. Let's just pretend. But so what will happen is as soon as alpha and beta cross, we know that something is bad and we have to start pruning. So what we'll do in the small example is I'll start, and just pretend this isn't here, it's gone. Okay. We'll start at the top and we'll say I'm going to start my alpha at negative infinity and my beta at infinity, and then I'll pass that information down to one of my children. And then what it's going to do is it's going to continue like recursively passing down until it hits the bottom. And when it hits the bottom, it can then like look through the actual values of its children, and it'll get the value of -30. And maximizers always increase alpha. So you take it from negative infinity and you try to increase it. And so maximizers are only allowed to update their alpha value. So remember that. So that maximizer says, I'm going to update my alpha to be -30. And then it's going to look at its next child, and it's going to say, I'm going to update my alpha to be -5. And then its like final value is going to be -5. And then it's going to pass that value up. And then when we get to the minimizer, since it's only allowed to update its beta, so maximizer updates alpha, minimizer updates beta. So the minimizer wants to bring that beta value to be as small as possible, but it can't affect the alpha value. So it started with its alpha at negative infinity, and it will stay there for now. And so what will happen is the minimizer says, now my beta is at -5. And so right now it seems like, well, the maximizer is updating one thing and the minimizer is updating another, and they're never even like coming into contact with each other. Why do we have these values, right? So here's what happens. Once the minimizer has received its update from one of its first children, the next children that it looks through are going to receive the current values of alpha and beta. And so this maximizer starts with an alpha of negative infinity and a beta of -5, right? And since it's trying to update its alpha, what will happen is it'll look through its first child and say, okay, this has a value of 5. I'm going to update my alpha to be 5. And since my beta is -5, now that alpha has crossed past beta, I know that I'm like not going to be chosen, and I don't have to keep looking any further. So just this like quick like comparison of alpha and beta and how we update it is enough to carry that knowledge that we were talking about before from our parents. So we've like turned that like wishy-washy idea into something more mechanical. So what will happen here is at this point I can say, okay, since I've crossed, like alpha and beta have crossed, I can then say I don't need to look anymore, and I can just pass whatever current value I have and kind of short circuit and send stuff all the way back up, because I know that stuff won't be chosen anyway. We get to the top and it finally returns -5. Does that make sense? Any questions about that so far? Yes.
So, I still confused when we will like update what beta.
Okay, yeah. So the rule is like alpha updates when you're in a maximizer and beta updates when you're in a minimizer, right? So what you would do is like if you are some node, like let's say you're a minimizer node, whatever values your children return, you'll basically look through and you'll say, is this smaller than my current beta? If so, I should update that and like update my like best value that I've come across, right? So what this minimizer at the top does is it says, right now my beta is infinity back here, and then when it gets its first return value back, it says, well, which is smaller, infinity or -5? -5, right? So then it updates its beta because only minimizers can update their beta. And then it says, well, I might be able to get something even smaller than -5, so I'll ask my next child. And then it recursively calls down to its like next child, and the next child does its thing until it eventually returns this value of 5. And then when the 5 comes back up, which is smaller, 5 or -5? -5, right? So then it will update its beta by not doing anything. So it could have updated its beta if the value we got returned was less than -5, but it wasn't. So it basically says, well, since -5 is already smaller, I don't need to update any further. Does that clarify? Cool. All right, so basically now let's just try out on our bigger example and see how it all like fits together. So what we'll do here is we're going to start with alpha and beta, and then we're going to look to our left child first, and we're going to pass those bounds down, and they're the same bounds. You always inherit your bounds from your parent. And then we're going to pass it down one more layer, and then like, which one's going to update at this point? Is beta going to update at this node, or is alpha going to update at this node? Beta, alpha. Okay, more for alpha. And then why would alpha be the one to update? Because it's a maximizer, right? So maximizer always updates alpha. So what will happen here is I'll say, which is bigger, -30 or -infinity? -30, right? So I update my alpha limit, and then I say, okay, now I'm going to keep looking through my children because -30 isn't bigger than infinity. Alpha and beta haven't crossed, so I can keep looking. So what I do is I say, okay, which is bigger, -30 or -5? I get to -5, and I say that one's definitely bigger than -30, but I still haven't crossed over infinity, but I've run out of children, so now I'm going to just send my value of -5 back up, right? So at this point, we update our minimizer's beta, because minimizers only update beta, and so the minimizer's alpha is untouched. So now what will happen is we're going to go ahead and say the minimizer knows that it can get like -5 already, so it's going to look for values that are smaller than -5. So it goes to its next child and it says, here are my bounds that I currently have, and it inherits the -infinity and -5 from the minimizer. And then it says, okay, I can update alpha because I'm a maximizer. It takes that 5 and it updates alpha because which is bigger, 5 or -infinity. At this point, alpha is bigger than beta, so we say, okay, it's time to prune off the rest of like what we have, and there's no need to look through the rest of the children. So we don't even look at the value 15. So even though 15 is bigger than 5, and a minimax tree that didn't have alpha beta pruning would have this node containing the value of 15. With alpha beta pruning, we don't even look at that value, so we just cut off early and we say, let's just return the value 5 because we have nothing, like there's no need to go any further than this. So we send that value up. Now this minimizer chooses between -5 and 5, and -5 is smaller than 5, so it can go ahead and pass that value back up, right? So when we go back up to the top, are our bounds going to update? Yes or no, if we're passing a value from a child up? Yeah, I see some nods, right? And then are we going to update beta, or are we going to update alpha? Yeah, alpha, right? Because that's a maximizer at the top. So we go and we update our alpha and say, now I'm going to look for things that are bigger than -5, and then I'm going to pass the bounds down to my next child. I'll get to the next child, and the next child will say, here's my alpha, here's my beta. I'll pass it down to the next one. They haven't crossed yet. So this will say, okay, which is bigger, -20 or -5? And it'll say, well, -5 is bigger, so although I'm going to hold the value of -20 for now, I'm not going to update my alpha. So I'm going to leave my alpha where it is. But I hold the value -20 because -20 is bigger than -30. So I take the value of -20 and I pass it back up without updating my alpha because I haven't found a better alpha. And then that'll give that value to the minimizer, which then says, well, now I can update my beta because minimizers always update their beta. And then it says, which is bigger, -5 or -20? We have an alpha that's bigger than our beta, which means they've crossed each other, and there's no need to keep looking, right? So at this point, I can say, well, I know that I'm not going to get chosen because my alpha has crossed my beta, and there's no need to look through any more children, and I can just short circuit and send this current value back up. So I'll go ahead and cross that entire subtree off, and I'll return the value of -20, and our final value at the top says which is bigger, -5 or -20, and we choose -5. Okay, any questions on how that worked? Yep. So that's like, so the question is like, how do we know that alpha and beta crossing is like when we don't need to look at the tree? That's like, so that's kind of like how it's set up, is the idea of like just these two values of like them crossing tells us that we can prune, because what we're saying is we're giving like bounds, right? So before we just had this idea of like, oh, my parents said I shouldn't look for any like value that's like bigger than this one or I won't be chosen. It's that same thing. You take like your parents send you down like upper and lower bounds, and if you move outside of those upper and lower bounds, like if you try to update your value like past those bounds, then you've basically told them that you're not going to get chosen because you're looking for something too extreme. So what'll happen is as this like game progresses, the bounds will get closer and closer together until it squeezes to one point. because like you have a maximizer and a minimizer, and like theoretically, if two optimal players are like playing at some game, it's going to be like close to a tie usually. So theoretically, they're like two values are going to get very, very close to each other, and you're not going to have like a huge range of possibilities. So you're telling your children, hey, don't exceed this, or don't like, what's the opposite of exceed? I don't know what that is. Go the other. Don't go too small or too big. So you're telling your children that with your bounds. Cool. Any other questions on alpha beta pruning? Yeah.
Can you explain again why maximizer doesn't choose 15?
Why it doesn't choose 15?
Yeah.
Yeah. So what'll happen is when we get to this point. So in a normal minimax, I would just say, oh, here are my values below me. I'm going to go through all of them, and then I'm going to choose the highest, right? But theoretically, if I tell you, hey, don't choose a number bigger than -5, and like let's say you have like an infinite number of children, like, and you know that the first value you get is bigger than -5, there's no need to even go through the rest of the children because you know you're not going to get chosen, right? So like if you have like thousands and thousands of options, but you know that like after the first option, none of the other options are going to get chosen, why look through them? So what we'll do here is it's the same idea of like I could have had many, many, many more children past this 15, but I didn't have enough space on the slide. So what happens is when you get to this value of 5, you say 5 is already bigger than the thing I've been told I can't get bigger than. And so there's no need to keep looking because I'm only going to get bigger and bigger values since I'm a maximizer. Because like I would have chosen 15 if I had the opportunity, but there's no point in getting the opportunity since I know that I'll never get chosen by my parent. Does that kind of make sense? Okay, cool. Any other questions? Yes.
Then wouldn't you always choose the first element since it's the smallest?
What about like here? Like in this one we choose, so we go through children until we get to like the best one because we haven't gone through our bounds yet. So the idea is like you can, like there are rules for things that you can and can't prune. Like there's like a general rule that you can't prune the leftmost child if you're going left to right because you have to arrive at one of the actual values before you can update any of your bounds. But like, so it's not a rule that you're always going to choose the left child. It's just because of the way the alpha beta pruning is, whichever direction you take first, you're more likely to choose that child than the other children, even if they have the same value. But it's not a hard and fast rule that you'll always be choosing one value over the other based on the positioning. Okay, any other questions? Cool, I think we're good for now. Awesome. So then here's some pseudocode, which pretty much if you're taking this class in the fall, which you won't be because you're here, what'll happen is like Hilfinger throws like this code up and then like it's there for like 3 seconds, and then like for project 2 you have to like make an AI, and like your job is to like turn this into Java code. But I just figured it'd be cool to like have here so you can see like what you don't really have to do for this class. But this is like the simple version. And this one is just like based on where I currently am. I'm gonna look through my children and find the maximum and then like send the value back up. So there's like a max and then there's a min. And then there's this like recursive one where you basically start at some point and then you like do the full alpha beta pruning all the way down up to a certain depth using like, you know, some like iterative deepening thing. So it's pretty fun. It lets the students make good AIs, but it's really, really hard. And the best way to debug this code is to delete it and rewrite it. So good thing we don't need to do that. But yeah, so if you're interested in it, you can go ahead and look at this. Other than that, you can take a short break. Let's do, what, 3 minutes? 5 minutes. Oh, 5 whole minutes. Then what'll happen is if you reset, all the changes go away because you have to yeah, because you haven't made them. So there's this little thing like, okay, like you've told me that I want to watch this, but we have committed. So if I try to like come back after the reset, like you want to like add I think yeah, because the amount there is that you lose that fire. So you want to. You want the area to have like it's not trapped. So the staging area we call that, but not trapped. So you want to act on it so it's not. It wants you to like add it. Yes. Yeah. So that would be, so then it would be fine to add it. I can choose the one.
Alrighty. Are we all back? Hi. Okay. Oh, is that better? Can you guys hear me? Yeah? Alright, awesome. Cool. So, before we go into the second part of the lecture, so basically what we're doing the rest of today is we're just going to talk about some review material so you guys are prepared for the midterm. But before we begin, let's talk about study like strategies and like kind of like how you're going to approach this, alright? So here are some tips. And maybe talk to your TA also to see if they have tips, because different people have different things that work for them. This is stuff that works for me and the other instructors, so maybe try these out this midterm if you didn't do as well on the previous one. So first tip, we've learned about a lot of data structures so far. So these are supposed to be the easy questions, these mechanical questions. There's going to be questions on the exam and on the quiz on Friday where you are given a data structure and you're told to perform an operation on it, and you need to draw what the data structure looks like after you perform that operation. All right. So for all of the data structures we've learned, make sure you know how to do that. All right. So that will appear, and that's supposed to be the easy point. So make sure you can do those. Okay. The second thing is we've learned a lot of data structures, and they have a lot of operations, and you need to know the runtime for all of these. So make sure you can tell me what the runtime is for different operations, and also know what assumptions are being made behind those numbers, right? It's not just linear, it's not just constant. There are assumptions that are being made, and depending on what those assumptions are, you might have a different answer, right? And so when writing midterm questions, like a very common thing to do is say like, okay, pretend you have this data structure, but this assumption no longer holds. Now what is the runtime, right? So you have to know like the reasoning behind the runtimes. Like don't just copy bigocheatsheet.com onto your like cheat sheet, right? Like it's not the numbers that matter, it's why those numbers are the way they are. Okay. Also know the difference between big O, big omega, and big theta, and when to use each notation, right? So if you guys remember from that worksheet, you guys had to copy that statement that said big O does not mean worst case, right? And then you signed your name. Do you guys remember that? Yeah, so maybe revisit that and try to remember why you signed your name there, right? So that's going to be very important. And so we're going to be asking you about the runtimes of basically everything on the exam. So make sure you know how to do that. And it's important because runtime is like the currency, right? It's how we can tell like how good something is compared to something else, right? Because as this course progresses, we're going to learn more and more data structures, and we need to know why like one is better than the other, when to use which in which situation, right? So this is how we can kind of count up the cost of what is better and what's not. Okay, tips for long coding questions. So I know those ones are the hard ones, so here are some tips on how to do well on those. First, like there's going to be a lot of text and it's going to be intimidating. So on your first read of it, just kind of briefly like skim the paragraphs, know what each paragraph is talking about, but you don't have to like grasp every small detail on your first read. Just know where stuff is so that when you get to that part of the question, you can go back to that spot and read it more closely afterwards. But just try to get the general gist of the problem when you read it the first time. All right. And then there's going to be quite a few blanks, and it's kind of like a puzzle, right? Like when you start the puzzle, you don't know where to start, but just try to figure out which pieces are the more obvious ones, right? Like for example, if there's a method header that says it's going to return Boolean, like you're probably returning true or false at some point, right? So that means one of the last lines of that method is going to be return true or return false or something like that, right? So just start filling in the areas that you know, or if you're running out of time, just fill in stuff that you know and start from there. Okay. Also, ensure the data types match up, right? So Java is a strongly typed language. It's not like Python. Everything is very like explicit as to what the type is, right? It's either a Boolean, it's an item, it's an actual object instance, right? So make sure that all those data types line up in your answer, right? Like don't return like node.value if you're supposed to return the node instead, right? Because those are easy points to be lost. But just quickly make sure that the data types match up and you'll be all good. And that also helps you solve the problem sometimes, because sometimes you're not sure what to return, but if you look at the data type, you're like, oh, it's a Boolean. It's got to be true if like there's two options, right? Like, or something like that. Like, there's only a certain number of options. Like, there's a certain number of variable names that are available to you, right? So the data type can give you a really strong hint as to what the answer might be. Okay. Also, there's going to be provided examples when we have those long questions, because we need to like make sure you understand what we're asking you to do, right? So there's often going to be a picture, or there's going to be like something that like, okay, if you put this into the function, this is supposed to be the answer. So make sure you use that example to kind of manually debug your code as you're writing your answer, right? And that will help you prevent off-by-one errors and stuff like that. And if there's not, if the example test case is too complicated or is just too long, like make your own simple test cases to try to like make your coding a little bit easier, right? And this also applies to general coding when you're on a computer, right? Like sometimes you're working on something and the given test case is just too complicated to debug or it's like too slow. So in that case, you want to make a simpler test case to help you, right? And the phrase is like you want to make a simple, rich test case. So you want to make something that is simple, something that's easy to run, but something that tests like different aspects of your program. So kind of what we were doing in lecture last week. Remember when I put like all these rainbow different like tree examples on the screen and said like we're going to test our code with those like all these different test cases, right? That's what you want. You want a bunch of simple ones that test different aspects. Okay? And here's a little story. For those of you guys who are around, like the BART system is like the subway system that kind of serves the Bay Area, and they've been putting out these new trains recently, and I'm a big fan of them. I'm secretly really into like transportation and trains and airplanes and stuff. I never got to do anything with it, but it's just like my childhood, like I don't even know what, it's not a fantasy, it's like my childhood, like I was intrigued when I was a child. But yeah, there's like all these new trains and you're like, wow, I just want these new trains to like be the only train that I ride on, but there's still like almost all the time, it's like all these old trains all the time, right? And you're like, when are they gonna pull out all the new trains? Well, I kind of was scrolling through this page this morning and it's just like, the reason why they don't do it is because they're not ready yet, right? And so they are testing the same way we are testing, right? And they're testing, it's pretty interesting. They're testing like on some test tracks. They're trying to try out different schedules, like running like maybe one train at a time to see like if there's going to be system-wide issues or if there's going to be failure cases on a larger scale. And they're slowly ramping it up, right? So even in the real world, like you never test with the largest example you have, right? You try to break it down into smaller examples and try to have these simple, rich tests to see if things are going to work or not, right? Like, what happens if we test it, going through that tunnel all the way to San Francisco? Is this new train going to hold up, right? So trying these small things at a time instead of deploying it all at once. So just try to think of this story when you're working on your exam. Like, you want to have simple, rich test cases, and this will help you out. This will make sure that you get off by ones, and this will help you make sure that you're doing the dot lefts and the dot rights correctly, all right? All right. Let's see, do we have more advice? Yes, general test taking strategies. Okay, so there are practice exams, and hopefully you know where they are. They're also on our resources page. They're through HKN website and the TBP website. So those are test banks where they have previous exams for previous summers and also previous semesters. Know what's in scope for this exam, and if you're not sure, you can always ask on Piazza. It's not like a secret. It's not like a guessing game. Like, if you're not sure if something's in scope, feel free to ask. But when you're doing these exams, most of the problems will be in scope at this point, but sometimes some are not, right? But when you're taking these tests, you just want to make sure you are simulating a real test-taking experience, right? So don't like sit there with the exam on paper and with the solutions on your computer, because like you're going to be tempted to look at the solutions before you've actually tried the problem, right? So you're giving yourself like almost like a fake crutch that you don't have on the real exam, right? So make sure you like close your laptop, print out the exam, and just do the whole thing like with the timer on, right? And like you can have your cheat sheet too, but just pretend like it's a real exam. And then when it's over, what Jackson recommends is that you can find your friend and argue about the answers before you even look at the solutions, right? So that's good because that allows you to defend your answer and make sure that that's what you really believe, right? And then once you've argued with your friend, and if maybe they like weren't convinced by your explanation, you can show them the answer key and be like, hey, like I had it right and you had it wrong, right? And it's actually not too bad if you get it wrong, because after you've argued about it, then you're like, okay, I got this wrong and I embarrassed myself in front of my friends, right? But on the real exam, I'm not going to mess this up anymore, right? So that's a really good way to practice. And just be honest with yourself as you practice. Like, if you got something wrong, like acknowledge it and go back and study it, and just don't look at the solutions too early, or else you're basically ruining the practice test for yourself, right? So you want to make sure that those stay valuable to you. Okay, and then the other piece of advice is pace yourself when you're taking the test, because the exam could be long, and there could be some details that you get caught up on, Right? This happens to me all the time. Like sometimes I'm doing a problem, and it's really annoying because you know you could do it if you had sufficient time, but at a certain point you're like, oh shoot, I've been stuck on this for 15 minutes, and there's still like so many problems left. Like at a certain point you need to tell yourself, I need to move on. I know I can do it, but I need to move on, or else I'm not going to be able to finish the other problems on the exam that I know how to do. Right? So just be conscious of your time. Have a game plan going into it. One good way to do this is when you get the exam, like put your name on the top of every page and just flip through and make sure you like get a glimpse of what problems are being asked. And you're like, oh, I really like trees. I'm going to do the tree problem first, right? So make sure you have time to do the problems you know how to do. And for the ones that you don't know how to do, like save those for last, or just limit the time you're spending on it so that at least you have the answers that you know how to do, all right? Okay. Oh, try not to leave anything blank, right? So it's kind of obvious, but kind of not at the same time. Like when there are long questions, or if you're just running out of time, like try to fill in the obvious blanks, right? So again, like if the return type is Boolean, the last line is probably return true or return false or something like that, right? So just match up the data types, see if you can fill stuff in. If it's multiple choice, or if it's like, what's the runtime? The runtime is probably constant, log, or linear, or something like that, right? So don't guess n factorial. Just guess something, and maybe you'll get it right? But make an educated guess, and try not to leave things blank, because if it's blank, it's wrong. Right? Oh, one more thing that's not on this slide. When you're writing big O and big theta, don't put the little hook on your O's, because I know some of you guys like to do that. So you're like big O and then like a hook, but then that looks like a theta. So don't be fancy and don't put that hook there. Just close your loop and that's an O, right? If there's a hook, we're gonna think it's a theta. So just be very clear with your handwriting and don't do any funny business like that, because like we want to give you the points, but we can't in that case, right? So just be very clear as to what you mean. All right. Any questions about like test strategy or test preparation or anything like that? It's a charger, okay. Cool. So let's talk about the actual concept. So here's some review slides. Basically what we're gonna do now is we're gonna talk really briefly. This is not comprehensive, and there's stuff that you've learned that's not gonna be talked about in the next I don't know, 30 minutes or so. But this is just kind of like a bird's eye view of what we've been doing in the big picture view. We're going to look at all the data structures, and we're going to look at the runtimes. Okay, so these are the runtimes we're going to look at, the operations that we're concerned about. So we're going to be caring about access, right? And so basically that is, how long is it going to take for me to grab an element at a specific index? If I give you an index number, how long does it take for you to give me that back? Okay. And then the search operation is looking through your data structure to see whether it contains an element or not. Insertion is how long does it take to insert a new item into the data structure. Delete is how long does it take to remove that element from a data structure. And this is assuming that you already have access to the target index or you have a reference to the node you're trying to remove, if applicable. Okay. All right. So let's look at our first one. Back to week 1, we had the array. Okay. So if you have a square bracket, that means the thing before the square bracket is an array. So here you have an array of integers. Okay? And if you have 2 square brackets, it just kind of applies in the same way, right? This second square bracket means you have a square bracket of you have an array of what came before it, right? So that means you have an array of int arrays, right? So a 2D array is just an array of int arrays. And you can instantiate them in a couple ways. So here, you can instantiate like this. You can say new int and specify how long the array is going to be. Or you can explicitly specify what the values are. And here, you're basically also saying how long the array is going to be. But in either case, the length of the array is fixed when you instantiate it. So in both of these definitions here, like you're specifying a length. This is length 6. This is length 4 because there's 4 items. And that cannot be changed after you've instantiated it. Right? The other important thing about arrays is that how long it is called the dot length. So it is a property of an array. It's kind of like a field in a sense, right? So it is not a dot length with parentheses. It is not a dot size with parentheses, and it's not dot size. All right, so that would be a syntax error if you put one of the other ones. And so kind of like the convention, how do you know what's length and what's size? Well, length is something that is fixed, right? Whereas size is something that can change. So for an array list, that can change size, and so that's why it's called a size, right? Whereas for an array, it's a fixed length, and so that's why it's called length. So that's kind of why there's that distinction there. Okay. All right. This requires some participation. So please, if you go pull out your web-compatible device, if you go to this website, try to come up with the runtimes of the operations for the array. This is great exam practice, so take a minute to do this. You can talk with your neighbor and do this together too if you want. All right, so here are the responses that you guys have. So for access, most of you guys said constant time, so that's correct, right? Access into an array takes constant time. All right, and if you remember, like this is kind of the apartment thing that I was showing, and that kind of like that lab example I was showing on the first day, right? So basically, in an array, it's fixed length, and it allocates a block of contiguous memory when it's created. So you also know like how wide each like spot is in the array because they're all the same data type, right? And so with some simple math, if you want to access the fifth element, you say, okay, I'm going to jump in memory forward 5 times the size of like one of those spots in for one of the elements, right? So if I want to take 5 big steps this way, then I'm going to arrive at my place in constant time because I can do that calculation and jump to that place in constant time in memory. Right? So that's different than in a linked list where like they're not in a contiguous block of memory. You have to jump from one place to the other. Right? Okay. For search, you guys said linear time, and that's correct, right? So if I'm looking for a value inside the array, it could be anywhere, so I need to traverse the entire array in order to find it. Okay. Insertion, you guys are kind of split between constant and linear time. So insertion, that's saying that we want to put it somewhere in the array. Well, it kind of depends what the assumptions are, and so maybe it's not too clear. But like so for your array deck, right? When you did your array deck, you could do it in constant time because maybe you had extra space in your array deck, right? For the raw array, like without all these like extra overhead and like these pointers and stuff, like probably your array has like all the items and it doesn't like have anything that's like garbage, right? There's no extra space available. And so if we're talking about something that's going to insert and force a resize, then that's going to be linear time, right? So if your array is already full, you need to add a new item in. You're going to have to allocate a new array with one more spot and copy everything over. That's going to be linear time, right? So if you're assuming your array is already full, you need to add something in. It's linear time. If you assume that you have space left in your array, then you can put it in constant time, like for your array deck. Okay, similar sort of delete. Like basically, if you care about making sure your array doesn't have extra space at the end, after you delete an item, you need to shift everything over and also, you need to reallocate a new array that's one smaller. You need to copy everything over and shift everything over, right? So again, if you care about not having extra stuff, it's going to be linear time. If you're okay with having extra space in your array, then you can just move your pointer one over and say that this item doesn't matter anymore, right? So for your array deck, again, that would be constant time. Okay? Great. Any questions on that? Yes?
This assumption is going to be explicitly stated on the exam, or is there like a formal set of assumptions that we should make for grades?
Yeah, for something like this, I would make sure that like you understand what the assumptions are. If it's not clearly stated on the exam, you can ask for a clarification. Yeah. And if we're not helpful, you can write your assumptions on the side too. Okay. Cool. Next up, we talked about, right, remember these pictures, right? So access into the array takes constant time. They're all apartment buildings. If I tell you I'm in the 5th apartment building, you can run over to that door in constant time. You don't have to like measure how many centimeters to walk or anything like that. Okay, and then also insertion and deletion into an array, like because it's fixed size, if you're going to like take something from the front and have to shift everything over, it's like Tetris, like deleting the bottom row, everything needs to shift down one, and that's going to take linear time. Okay, now let's talk about the linked list. So the linked list, we've talked about the linked list and a couple improvements on top of it, right? So the very bare bones linked list is the naked linked list. The naked linked list is just a node class, so it's kind of similar to what you probably saw in previous classes, like if you took 61A, it's like just the node, and it has an item and a next, and that's it, right? And those are hard to use because if you're going to use that data structure, you need to know how to manipulate it yourself, right? And so we did one better than that. We did encapsulated linked lists. So basically what that was is we had a linked list class. It had a node class that was nested inside of it. And basically the outer class provided a set of methods, or like an API, for the user as to what methods could be performed on it. So you provide an insert method and you do everything behind the scenes for your user, or you have a delete method and stuff like that. Right, so that's encapsulated linked list. It's better because it's easier to use and it has an abstraction barrier that hides the user from all the details of the linked list. Okay, we also talked about a sentinel. The purpose of a sentinel is to eliminate the need for null checks, right? Because if you don't have a sentinel, you're always like, okay, like I want to go to the dot next to this node. Oh, but only if it's not null, because if it's null, I'm at the end, right? Like you always have to do that check to avoid getting a null pointer exception. But if you have a sentinel and it's like a circular design, so basically the last node goes back to the sentinel, then instead of being afraid of like stepping on something that's null and calling it, like accessing a field of it, you can just go all the way around and make sure you're not at the sentinel again, right? And so this eliminates the need for null checks. Okay, and then the last improvement we had was doubly linked lists. And so basically all that meant is instead of just having a next pointer, we also have a prev pointer. Okay, so those are the improvements we talked about. All right, so you know what's next. Go to this link here and tell me what the operation runtimes are for both a singly linked list and a doubly linked list. It doesn't matter if it's naked or encapsulated because that won't change the runtime. And it doesn't matter if it has a sentinel or not because that won't change the runtime either, right? But there could be a difference between singly linked lists and doubly linked lists. If you're not sure, feel free to talk to the person next to you, even if you don't know them. Introduce yourself, try to make some friends. You don't have to hide behind the screen here. Okay, great. So access into a singly linked list is linear time. And that's because, unlike for the array, you can't just compute where to jump in memory and jump there right away. Because the links are in different places in memory, you have to go to the first one, and then you have to say, okay, where is the next node in memory? Oh, you follow the dot next. Oh, it's like way over here in memory. And then you're over here, and you're like, okay, where's the next one? Oh, it's way over, like, you have to jump from place to place. You can't just jump to the right place in memory, which is why even if you know what index you're going to, you have to go through all the nodes in linear time, okay? It's like my airplanes, and right, going to New York, and then it gets delayed, and then even though I just want to go from San Diego to Oakland, it's super slow because it got delayed, right? Yeah. Okay, cool. Search is indeed linear time because same story, like if you, like there's no organization in the linked list, it's not sorted or anything like that, right? And so you're gonna have to go through the entire linked list and follow every node until you potentially find what you're looking for. Okay, insertion, we're split between linear time and constant time. So to insert something, we're making the assumption that we know where we want to insert to, and that we have a link to the node that we want to insert after. Okay, so because otherwise it's the same. It's the same as like the one before that, right? Like if you didn't have that, you would have to traverse to the place where you want to insert, and then like do your insertion thing, right? But assuming we have a reference to the node where we want to insert after, then all we have to do is take that current node that we're at, we make a new node with the item that we want to put in that node, and then we assign the current nodes next to be the new node we made, and then we assign the new nodes next to be the one that came after it originally, right? So that's just some pointer manipulation, and pointer manipulations take constant time. So assuming we already have a reference to that place where we want to insert into, we just perform a little bit of surgery and it's fine, right? Of course, if you don't have a reference to that node you want to insert at, then you need to traverse to it, and that will take linear time, okay? So maybe that's why we're split on this one. Okay, for deletion, it's kind of a similar story, except, so if we have a reference to the node where we want to delete, if we want to delete a certain node and we have a reference to that node, well, how are we going to get rid of that? We need to, let's see. Well, basically what we need to do is we need to find the node that came before it and reassign its next to not point at it, but to point at the one that came after it. The problem is, if we have a reference to the current node, we can't go to the previous node easily, right? Because there's no pre-pointer for a singly linked list. So for a singly linked list, in order to get to the node that comes before it, you have to go to the beginning and traverse it until you get to the one that came before it, and then you can do your surgery, right? So because of that problem, because we don't have access to the one that came before it, like you'll have to spend linear time in order to get it. Okay. And so basically for a doubly linked list, all the other answers are the same: access, search, and insertion. They're all the same because if you could do it quickly with a singly linked list, like a doubly linked list is the same thing as single, but also with a prev, right? So there's no way it could be slower because it can do everything a singly linked list can, right? So the first three are the same, but for deletion, because we have a prev pointer, because we can easily go back one node in constant time, that procedure is going to take constant time. Okay, if you've been on the bigocheatsheet.com, bigocheatsheet.com, you will see that it disagrees with me. So it says that a singly linked list is going to take constant time for deletion as well, right? So someone's wrong. Either I'm wrong or they're wrong. Or we have different assumptions, right? And so that turns out we do have different assumptions. So if you follow like this link here, it goes to a Wikipedia page, and for their deletion, they're assuming they have a reference to the link that came before, right? So if you have a link to the one that came before the one you want to delete, then of course that'll be constant time, right? Because then you don't need to go to the front and get to it, right? So we have different assumptions here, so be very careful. Like, don't just copy this number because this would be wrong on our exam because we're assuming that we don't have a link to the one that came before it. Okay. Are you guys all familiar with this website? It's called bigocheatsheet.com. It has this very nice table, right? So it's very nice. Don't just copy this. Make sure you understand where these numbers come from because, as we just demonstrated, there can be discrepancies based on what the assumptions are. Okay. So be very careful when using this, but this is very helpful. Okay. Awesome. Let's go carry on. Okay, So here are the rest of the cool pictures we had from this awesome slide that's so aesthetic. Right, so accessing in a linked list takes linear time because just like the airplanes, you have to jump from one node to the next, and they're not in a contiguous block of memory. For insertion and deletions, all you have to do is put a sign in the road saying that this road is closed, go to the next road over, right? That takes constant time. You don't need to like shuffle everything over or anything like that. Okay. Alrighty. Trees. So we spent a lot of time talking about trees recently. So tree is basically kind of like a linked list, except instead of only having one child for each, like having only one next, like a node can have as many children as you want, basically. All right. Of course, there's some extra conditions. So for example, no cycles are allowed. So basically, you can't like follow some nodes and basically end up where you were at before. Like it has to be like, it has to be acyclic. So there can't be any cycles in your tree. Otherwise, that's not a tree. Okay. We also have access to a root. Okay. And also, all the nodes have to be connected somehow. Like you can't have nodes that are not connected to your root, because otherwise that kind of be like a forest, not a tree, right? Okay. That's a real math term. It's not a joke. Okay. So we also learned about binary trees. So binary trees are a tree with this restriction that you can have at most 2 children per node. Okay. We've also learned about a binary search tree. So a binary search tree is a binary tree with this search criteria on it. And the search criteria basically says that for any node in the tree, everything in the left subtree has to be smaller than that node's value, and everything in the right subtree needs to be bigger than what's in the node's value. And this needs to apply recursively throughout the tree. That has to apply at every single node in this tree. Okay. We also learned about balanced search trees. So note that these both start with B's and they have S and T's in them. But when we say BST, that means binary search tree. It does not mean balanced search trees. Okay, so don't get confused. BST means binary search trees. Okay, but about balanced search trees, we've learned about 2 different ones in this class. We learned about B trees, and B trees are 2-3 trees or 2-3-4 trees. That basically says that every node can have 2 or 3 children, or it can have 2, 3, or 4 children, right? That's what that means. Okay. We also learned about red-black trees, and we learned that 2-3 trees and left-leaning red-black trees have a 1-to-1 correspondence. So that means for every like unique 2-3 tree, there is exactly one unique left-leaning red-black tree that maps to it, right? So it would be nice to know how to convert between the two, right? That is a very easy mechanical question that could be asked. Okay, but basically these are self-balancing trees. These are like binary search trees, but they ensure that they always stay balanced because that's beneficial for runtime purposes. So speaking of runtime, let's figure out what the runtimes are for BSTs and also balanced search trees. So go ahead and go to this link here. We're only going to do search and insertion for these, right? Because access doesn't make sense because like that's kind of like the lower abstraction barrier. You can't index into a tree really, right? And also deletion is kind of complicated, so we'll talk about it afterwards, but I won't ask you to do it right now.
binary ways or
We'll give you about 15 more seconds. If you haven't submitted yet, submit something. So pretend it's like an exam. Don't leave it blank. Give it your best guess and just commit to an answer. Okay, cool. So for a binary search tree, a BST, most of you guys say log and some say linear. So again, it kind of depends on the situation, right? And so in this case, it's kind of like a best case, worst case deal, right? If you have a binary search tree and it's like reasonably well balanced, then you'll have approximately log runtime for search on average, okay? However, if you do not have a binary search tree that is well balanced, for example, like it is valid to have a binary search tree that's like a 5, and then its dot left is like a 4, and its dot left is a 3, and its dot left is a 2, right? Basically, you can have a binary search tree that is very spindly, right, rather than bushy. So if it's very spindly, it's basically like a linked list, and so its runtime will be like a linked list, right? So if it's a spindly binary search tree, it's going to behave like a linked list, and it's going to have linear runtime for this. Otherwise, if it's bushy, then it's going to have a log runtime. Okay. Very similar for inserts, right? So for insert, we just have to like locate where it's going to be in the binary search tree, and we make a new node for it at that spot, right? So again, if it's a bushy binary search tree, that will take log time to perform to get to the bottom and find its rightful place. Or if it's spindly, it's going to take linear time to get there. Okay. So I'm proud of you guys. You guys have both of the two answers that I was going to say, right? So this one is the average case, and this is the worst case. Okay. So also, just to review, right? So the best case is theta of log n, and the worst case is theta of n. All right. The runtime, right? The runtime is big O of n, big omega log n. Right? Oh, it got really quiet all of a sudden, right? So if you're asking for best case or worst case in specific, it is exactly theta n or theta log n, right? If you ask what is the runtime, then you need to give a big O and a big omega that gives you the range that describes what the runtime is, okay? So it depends on what the question being asked is. I put a story about my friend Caitlin and Gabe eating steak, if you remember that, right? So reread that if you don't quite understand, but when you're asked for best case or worst case, you need to say it's exactly this much. It's theta this much, right? If you're asked for what the runtime is, it's this range. Okay. Okay. Cool. All right. Balanced search trees. Basically, it's the same story as a binary search tree, except we know it's going to be bushy because a balanced search tree is self-balancing. So because it has these self-balancing mechanisms, it's always going to be bushy or basically bushy, and so you're going to have log runtime in all cases. Okay. So the runtime would be theta log n. The best case would also be theta log n, and the worst case would also be theta log n for a balanced search tree for these operations. Okay. Awesome. All right. So what about deletion? Okay, deletion is kind of complicated. I'll give you like kind of the lowdown because it's kind of interesting. It is kind of like, it's kind of difficult. So you guys might remember this picture from the spec. So this is deletion from a binary search tree, right? And so in order to delete, like say this item here, well, you need to make sure that search invariants of the binary search tree are maintained, right? And so whatever, like you can't just delete this node and like leave this tree without a root. You have to put something in its place, right? And so how do you know what number to put in its place? Well, it's this one that's circled, right? So you know it because it's circled. You also know it because it's called the in-order successor. It is the in-order successor because it is the next item that, it's the smallest item in this tree that's bigger than the one that's being deleted, right? 5 is the smallest thing that is bigger than the 4 we're deleting, right? And it's always going to be in this position. So the in-order successor, you get to it by going dot right once, and then you go dot left as many times as you can until you get to the bottom. And that's where the in-order successor is going to live. So what you do is you can remove this, and then you can basically put it at the top, And that's like the simple story as to how you delete from a binary search tree. Okay. Yeah, so that's fine and dandy. But so this is called hybrid deletion. You can read more about it and make sure you know how to draw them, right? But in terms of runtime, like how do you like assess the runtime of this deletion? Well, it turns out like there's like a slight asymmetry here. Like it's not perfectly balanced, like how you always go to the in-order successor and you plug it back up. And like there's been a lot of studies on this and a lot of papers that have been written about this stuff. Apparently it's not easy. And basically, when you do a single deletion, you're messing with the symmetry of the tree. And so it's not going to be, even if you had like random insertions to make a bushy tree to start with, doing a single deletion is going to mess with this perfect symmetry of the randomness of random insertions. And so subsequent operations are not going to take log time. It's going to take square root of n time. So you don't need to know how to derive that. You don't need to know like why that is, but just kind of know like if you do deletions with a binary search tree, it's going to mess with the symmetry and you won't have log n time. But if you never delete, then it will be log n time. Okay? So it's just kind of like interesting thing to know. Yeah. Don't worry too much about this, but you can click on this paper and kind of like, it's very complicated. I can't understand it either, but like you can read it and you can get a sense for what they're talking about. Like basically, what they're doing is they're going to assess like how the expectation of the height of the tree changes when we perform a single deletion from the binary search tree using this method, right? And they basically conclude that the expectation is not the same as it was before. Okay. Great. So now we're going to have Christine come up. She's going to talk about the last two data structures you learned, hash tables and heaps.
Hello? Hello? Does this work? Can you guys hear me okay? Yeah? Okay, cool. So we just have two more data structures that we want to cover. So the first one that we want to do is the one that we covered this Monday, which is called the hash table. And it's really just a combination of what Matt talked about. It's an array of linked lists. So it's basically combining the good parts of both of them and making something that's really, really good. All right, so it's here's a recap of the array and a linked list. So remember, accessing in an array takes constant time. Inserting and deleting from a linked list can also be in constant time as well. So we're basically taking these two parts of these two data structures and combining them together such that we get something that's super good. All right? So just as a refresher, this is what a hash table is. It's an array of linked lists. Every single index of the array, we're going to be using it to store elements, right? Those are going to be what we call buckets, and we're going to store each of our elements inside these buckets. We're going to figure out where each element goes by using hash code modded by the array length. We talked about the hash code in lab on Monday, but it's essentially like the identifier for the object. So you're getting the identifier for the object, figuring out which index it should go into, which is modding it by the array length, and then putting it in that spot. All right, so we will have it's possible that multiple things can go into the same spot, so we deal with that through what is called external chaining, which is where the linked list part comes in. So we have a bunch of arrays. Each of those are the buckets, and in every single spot in the array we will have a linked list. So if there are multiple things that go to the same spot in the array, they can just chain together, which is why they're called external chains. Okay, so just remember, this was one of the questions on the worksheet too, that if you modify an inserted item, it's possible that you might not be able to get that back, because remember, the way that we put items into our hash map or a hash table is using that hash code. So if you've modified it and then you try to find it again, it'll probably be in a different spot than you expect it to be in. So just make sure you try not to modify things after you've put them inside the hash table. Okay, so a lot of this runtime goodness comes from a few assumptions that we have to make. So we'll mostly be assuming that there's going to be like a good spread, which involves having a good hash code that spreads things out really well. Having a good spread, a good load factor, and then in that case, hopefully our linked lists will end up being short. But note that if we do ask you any question on the exam regarding hash tables, you need to make sure what assumptions are there, right? Because not all the time can we assume that hash codes are going to be good, or that we're going to be using linked lists as the chains, or that we're going to be using certain parts of this that you are familiar with. So make sure you know what assumptions are being made and what assumptions that you have to account for as well. Because if our hash code is bad, that can lead to some different behaviors, right? So we will assume that if we have a good spread and we have a good load factor, that our linked list will be short, which is where these next runtimes will come in. Okay, so we're going to do this 2 more times, so one for this one and one for the next one. But please go to this yellow key over here and try to figure out what the search, insert, and delete runtimes are for a hash table. All right, so we're assuming that there is good spread, so assuming that those linked lists will be short. So go to that link, put in what you think for those 3 methods, and then we'll talk about it in a little bit. Okay, cool. So let's regroup. So let's talk about each of the runtimes for these. So I'm looking at the results over here, and you guys have pretty much got it. So let's just walk through them all together, and we'll start with the search runtime. So the search runtime, most of you answered constant time, which is good. So let's go over basically how that will work and why the runtime is the way it is. Right. This is based on a few assumptions that we have to make, so we'll be outlining those assumptions as you go through this as well. So remember, when we search for any item, we first have to compute that hash code of that item. That will happen in constant time, so we don't have to worry about how long that'll take. This is actually assuming that this will run in constant time. Sometimes it might not, but assuming that the hash code runs very quickly, we can assume this part will be pretty fast, so that part's constant time. Next thing is we'll jump to that bucket in the array. And just as Matt was talking about before, jumping to that bucket is going to take constant time, so we don't have to worry about that part. And then the last one is looking through the linked list, right? So that's the last part of this. Everything was constant time up until this point. So looking through the linked list, this can take a variable amount of time, and this is depending on how long those linked lists are. So the main 2 answers were constant time and linear time, and those are basically both correct, but you have to be careful about what assumptions you're making. So if we're assuming that our hash code is good and there's a good spread between everything, we can assume that our list will be short and that going through this last step will be really fast. All right? But if we assume that our hash code was really bad and everything went to the same bucket, then that's when this could potentially be linear time. So there's 2 different options here. We're going to be assuming for this exercise that everything is going to be very well spread out, so these linked lists will be short. But there is another option that if those linked lists are long, this will end up taking a lot longer. It'll take linear time. All right? All right, does anyone have any questions about that part? All right, perfect. So the next few runtimes are actually very similarly derived. So you'll see a lot of copied and pasted stuff up here, but insert is also going to be theta 1. All right, so we're going to do the same process. We're going to compute the hash code in constant time, jump to that bucket in the array in constant time, and then we're going to do the insertion into that linked list. All right, so we're going to look through the linked list. It'll be constant time if it's short, and if the item is not there, we're going to append it to the list. Right, and we talked about appending to the list. That will take constant time if you have already gone through it. So here, this runtime will essentially depend on how long those linked lists are. And if we have something that's a good hash code, we know that those linked lists will be short. All right, so this is going to be constant time as well, unless the hash code is bad. Okay? All right, any questions? All right, perfect. And then the last one is removing. So removing is also in constant time for a very similar reason. And you guys have basically got all this down as well. But we're going to compute the hash code again in constant time, jump to that bucket in the array, and then we're going to look through that linked list. All right, it'll take constant time or linear time or however long it takes depending on how long those linked lists are. And if the item is there, we'll delete it from the list. That'll take constant time like we talked about before. But the main issue with, or not the issue, but the main factor that gets you that runtime is iterating through that linked list. So as long as those lists are short, or as long as whatever data structure you use to chain is very small, then you know that you can do this pretty fast. Okay? All right, any other questions about hash tables in general? Yeah?
If you insert, don't you have to potentially resize the array?
Okay, so the question was, if you have to resize the array, like what happens in that case? And that's a really good question. And that's something that we've actually omitted from these runtimes. So in general, we're going to think about, I guess this is another assumption that you'll have to make. We are assuming, we haven't written it down, but that resizing will not occur when we insert. But in the event that our load factor does get too big and we have to do a resize here, that's when the linear time will come in, and you'll have to rehash everything to go into the new spot, make that new array, and that will take the linear time as well. So good catch. That's not something that we're going to assume that's going to happen here, but that is something you'll have to think about on the exam as well. Yeah, thanks for pointing that out. Yes? All right, so the question was, what is the difference between a hash table and a hash map? So usually we will think, I personally like to think about hash tables as being like without the key value mapping, but in Java's implementation, hash tables and hash maps actually both have a key value mapping, which makes it kind of confusing. We won't really test you about like, tell me the difference between hash tables and hash maps, but the main difference is like a synchronization thing, which you don't have to worry about. This is more 61C, 162 kind of concepts, but if you have concurrent operations to one data structure versus the other, you might get differing results. So you don't have to worry about that, but that's the difference between them. Mm-hmm. Alrighty, any other questions? Okay, perfect. So the last thing that we'll talk about is heaps. So I'll go over this like in slightly more detail because you just learned it yesterday, and this is actually my favorite thing to teach ever. So yeah, let's talk about heaps. Remember that heaps are basically trees. So we talked about trees earlier, but they have two additional properties. Does anyone want to share what one of those properties are? Just raise your hand. What do you guys think? Yeah.
All the children of the parent need to either be larger or smaller than the parent.
Exactly, perfect. So all the children have to either be all larger or all smaller than the parent. There's one more. It's kind of about the structure, the special word. Yeah.
It has to be complete.
Perfect, yeah. The last one is that it has to be complete. So we'll see examples of this, but the two additional properties is the completeness property. So all available positions for elements must be filled in the tree except the ones that are in the bottom level. And the heap property, which was mentioned over there, that each element must be smaller than or larger than or equal. So in this case, they can actually all be equal as well to all of the children. We'll be studying binary min heaps in this class and for the rest of this lecture, but just note that you can also have like trinary min heaps or like heaps with 4 children or 5 children or however many that you want. We'll be studying them with just 2 children and that they follow the min heap property. Okay, so here are just a few examples of a heap. This thing with just one item is a heap itself because it follows those 2 properties, right? There's completeness, kind of trivially complete because there's one thing, but it also follows the min and max heap property here. Here we're going to just be looking at all the heaps using the min heap property. Right, next one, this is also a valid heap as well. Notice that it's complete, so all the spots are filled up and the min heap property exists for every single element. This one works as well because even though it's missing one of the items, they're all shifted to the left. Like all the items at the bottom level are shifted to the left. So that's what a complete tree is, and you can check that all the values also follow that min heap property. Here's an example of something that is not a heap, and because it's missing one of the properties, right? So which one is it missing? You guys can shout it out. Completeness, yeah. So completeness is the one that's missing over here. It's because there's that item that's missing right in this spot. 2 should actually be shifted over 1 spot this way, so it fills up right over here. And then the last one, this one also is not a heap because it doesn't follow that min and max heap property. Right? There's this 5 and this 4 right over here, so there's a problem between these 2 nodes. It should actually be the 4 on the top and then 5 on the bottom. All right? Okay, so any questions about heap properties or what they look like? Yes?
So repeat elements are allowed, not every element is to be unique or to be.
Yeah, that's a good question. So it was, can repeat elements be allowed in heaps? Generally, yes, they can be allowed. In the lab, we specifically told you not to allow duplicates because this heap will be used for project 3, which requires like special things about the heap. So just for this lab, we said no duplicates, but in general, you can have duplicates. But yeah, that's just another assumption that you have to be clear about, whether you can have duplicates or not. Here we can, but in the lab and in the project, we probably won't be. All right, anything else? Okay, perfect. So I'll just keep going with the summary of what this data structure is like. So another thing we figured out was how to represent these heaps. You could create a tree of some sort, but we found a special way to use arrays to represent a heap using some form of special indexing. So here's kind of the rules. I'm not going to go over it without having an example up here, but this is, let's say this is our heap. If you have any item at any index, let's say I, the left can be found at index 2 times I, the right can be found at index 2 times I plus 1, and then the parent can be found at 1, or at I divided by 2. Right, so we can see this is the array representation of this heap right over here. So 0, we've shifted everything over by 1 just to make the indexing work out a little nicer, but this 0 is at index 1. Its 5 child is to the left, so we know that it should be found by going to the 2 times 1 index. Right, so 2 times 1 gives us 2. 5 should be at the second index, which it should be. And this actually works for all the lower levels as well. So 5 has a left child, which is 8. 5 is at index 2. So we know that the 8 should be at 2 times 2, which is 4. And we can see that the 8 is right over here. All right, so this special indexing will really help us access each of the elements really fast in the heap. So we can do some special operations on it later on. But this is the representation that we'll be using. It's an array. Special indexing allows us to basically hop through the branches like we would in a regular tree with following the pointers. Okay? All right, any questions about this representation? Cool. And then we have one more. So note that we will always want to access the minimum element of our heap. This is just what the heap is really good for because of that heap property. So every single element will either have all children less than or greater than it. So we're studying min heaps in this lecture. So every single thing that's below the root will be larger than it, right? So heaps will allow us to access either the minimum element all the time or the maximum element all the time. And here are the methods that will help us do that. So we did these all in lab yesterday, but they're called the insert, which adds an element to the heap, the remove min, which will remove and return that smallest element, and the find min operation, which will just return the smallest element. Right? So we worked with these three. This is basically what the heap is made up of, and this is how you can create things, create heaps, and get those items out of it. Okay, so now we have one more. This is the last yell key of this lecture, so just bear with us on this. We did this in a discussion worksheet yesterday, but let's try to rederive it. But go to this yell key and try to figure out what the worst case runtimes for insert, remove min, and find min are. Okay, so I'll give you like a minute and a half to do that, and then we'll go over why it is the case for them. Okay, so let's bring it back and let's talk about the runtimes for these. So looking at the responses, you guys did pretty well on this, so we'll just quickly go over all the runtimes for all of them and the reason why that they are the way they are. So we're going to start with insert. Insert's the very first one, and inserting will actually take log n time, and we'll see how this works. All right, so remember that we have those two properties. We have completeness, and we have the min heap property, which we always need to make sure are satisfied in a heap. Right, so remember those two things have to always be satisfied, and the way that we do these operations actually go in line with trying to satisfy those properties as we go. Okay, so the first step when we try to insert an element is we first just place the element at the first free space in the heap. So that would be the first spot on the bottom level, which would also correspond to that very last spot in the array that's free. All right, so this satisfies the completeness property first off. We don't really care about the min heap property yet, but as long as we satisfy the completeness property, we know we're getting closer to the goal. Right, so first we do that, and that will take constant time. Remember, adding to an array will take constant time. We're assuming we don't have to do any sort of resizing here, so just adding to the array will take constant time in this step. And then the next thing that we'll do is we'll bubble the item up. So you might have heard like bubble up from the lab yesterday, but bubbling just means keep trying to switch the element with its parent until it is a valid heap. All right, so this is us trying to satisfy that heap property. In the worst case, that will end up having to go all the way to the top, and that will take as a total of log n time. Right, so the reason why is it log n to begin with? We didn't really cover that too much, but remember that our tree or our heap is complete. Complete meaning all the spots are filled, so we don't have anything that's spindly. Right, so the total height of our heap will not be more than log n, so the amount of swaps that we'll have to do will not exceed log n. So this will take constant time. This will take log n time in the worst case. So this will total end up being log n. Okay. Any questions about that? All right, cool. So let's go into the next one. Next one is the remove min, and that will also take log n time for a similar reason. So first thing we have to do is satisfy that completeness property. So the first thing that we'll do is we'll swap the root with the last item in the heap. Right? So you might ask, oh, why do we do that? Because that doesn't really make much sense. But we want to get the root item off. So by swapping it and then removing that item, we're actually satisfying that completeness property because the item that we removed was in that last spot of the heap. Taking it out means that our heap is still complete. It might not satisfy that min heap property, but we know that the completeness is there. So that's the most important part, is that we're getting closer to the goal. So doing that swap, taking that item off, will satisfy the completeness property, will give us the minimum item, and will only take constant time. Right? So the next part is we're going to bubble down that new item that we swapped up there because we're not sure if that swapping up that item will actually be good. It could be that that was actually the maximum item that we put at the top, so now our min heap is all messed up. But we would swap, once we swap it, we're going to bubble that item down. What bubbling down means is that we're just swapping it with its children until we get a valid heap. All right, and again, same reason for why it's log n. The tree is only going to be at most log n height, so we'll have to do at most log n swaps. Okay. Right. Any questions about this one? Yes?
Why do you do the swapping between the last item and the root in the first place? Why don't you do like a bubble down thing of the minimum?
Okay, that's a good question. So why do we swap, why do we do this in the first step where we swap the root with the bottom item and then we bubble up like the new item that's now in the root? The reason why we do the swap is because the completeness property, I think, is the harder one to satisfy. If you deleted the root somehow, how do you make sure that it's complete again? Like you need to fill that spot with something, so we don't really know what to fill it with. So there are many different ways that you could approach it, but one way that we like to do it is we satisfy the completeness property first, and then we will satisfy the min heap property. So the completeness is first, and that would be swapping the root with the last item in the heap, and then removing that new last item, which was the previous root. Okay, does that help a little bit? Yeah? Okay. All right, so the last operation is the find min. That one will take constant time as opposed to these log n operations, and that is because, remember, we're following the min heap property here. So the smallest item will be at the top of the heap all the time, so we'll just have to return whatever is there. We don't have to change the structure of the heap at all. So returning the item at the top of the heap, that's the first index of the array, and that'll take constant time. Okay, so just as a reason, we did introduce heaps with priority queues. They sound very similar, so I just wanted to cover why we have both of them if they sound very similar to each other. So just remember that the priority queue is not an actual thing. You can think of it as an idea that we want to store items based on something else other than when they were inserted into the line or into the queue. So for example, we saw in the lab that we were trying to model an emergency room or like a refrigerator or something. We can't just use a regular old stack or a regular old queue for this. We need to be able to associate items with a certain importance. So that's where this idea of a priority queue comes in. Is that we want to be able to associate things based on how important they are to us. So we created this idea that we want a priority queue. On the other hand, so idea is synonymous with the term abstract data type. So you've probably heard this in a previous, last lecture or something, where we talked about ideas of things that we want. Priority queue is another example of that. Okay, so a heap, this is actually where the implementation comes in. So it's a real life thing. It's a structure that helps us order elements, so the minimum or the maximum is always easy to access. So in this case, this is actually one thing we can use to implement our idea. Right? So remember, priority queue is just an idea. We can use a heap to implement this idea of having something organized by how important it is. And it's kind of created for this process, so it's probably one of the best ways you can represent a priority queue. But just note that there are a whole bunch of other ways you can implement a priority queue, but Java and us will use a min heap to implement a priority queue. All right, so this is when we refer to the term data structure. Data structures are usually the implementations of things. So trees, those are actual living things. And We have lists, like those are actual lists and arrays and trees and heaps. Those are all real implementations that you have worked with. And these are not just ideas. These are actual things that you had to code. So this is what we usually refer to as data structures. All right, so just as a recap of what we did in lab, we made this thing called a min heap PQ, which implements a priority queue using a min heap. But we could have also made like a linked list PQ, which implements a priority queue using a linked list. We could have made a balanced search tree PQ that implements a priority queue using a binary search tree. But just note that the reason why we had all these weird classes, and there's 3 different classes that kind of do the same thing, is because we want to illustrate this relationship here, is that priority queue is just an idea. That's why it was an interface during lab. And the thing that we actually are implementing is a data structure, which is our min heap class. Okay? So I think that is all from us. Do you have anyone have any last minute questions about heaps or priority queues in general? Okay, perfect. Well, if you have anything else, please let us know. We're going to be sticking around for a little bit afterwards, so if you have any questions about anything, feel free to come up and we'll be able to answer those for you.